let's talk about photons. You might notice this book is really short, and this video is too. The last two have been a marathon watch. That should give you some indication of the amount of stuff that you need to know and that you need to learn. Really, I was toying with the idea of releasing this in the middle of the week so that you could spend some more time looking back over 414 and 415 on young slits and stationary waves. And I'm going to ask that all of you complete a revision task. Remember when we finished electronics over Easter, I asked you to do 1 on the basics, the quantities, and 2 on circuit problems. You should have 2 nice clear revision posters on electronics showing you the stuff that you have to know and the more complicated circuit problems. Same with waves now. We've finished it. There's no more wave stuff. So I want you to complete 1 on the basic stuff, so V equals F lambda, electromagnetic spectrum, wave behaviours, wave properties, everything up to kind of 4.13. And then another page on the new ideas in waves. So that's superposition, stationary waves, Young's double slits. They are really, really in-depth ideas. And I think when you look at the stuff that comes up in exams in year 13 on waves, it always ends up talking about a Young's slit or a stationary wave, or it will link it into photons, and that's what we're going to start today. To start, I want you to think about this. Do this exercise, right? Refresh your memory of the EM spectrum, list them in order. Sing the song to yourself, it's good fun. And use your brain to try and perhaps label it in terms of increasing energy. If you're not sure about that, think about danger. Take a guess at the relationship between energy and the frequency of it. So I'll keep it short because there's not much to say really. In this video, all I'm going to ask is, what is a photon? And how do I calculate the amount of energy that it contains? So let's have a look. EM spectrum goes radio, micro, infrared, visible, UV, X-rays, gamma rays, right? Not even struggling with it. It's easy. The wavelength goes that way. Radio waves have the highest wavelength. Microwaves, infrared, they've got long wavelengths. Gamma rays, X-rays have really short wavelengths. All of them travel at the speed of light. V equals F lambda tells us that frequency and wavelength are inversely proportional. So frequency goes in the opposite direction. Radio waves, really low frequency. Gamma rays, really high frequency. Energy goes the same way as frequency. The reason why X-rays and gamma rays are dangerous is because they carry the most energy. Radio waves, microwaves, you're swimming in them right now. You know, the Wi-Fi from my router, the radio waves to my phone, the radio, the TV, all of those signals are going through me right now doing nothing because they carry virtually no energy and they don't care about me being there. So, let's look at photons. Electromagnetic waves transfer energy, and what we find is actually this energy that they transfer, it exists in discrete packets. We give a posh name to those packets, quanta, and they are photons. So a photon is just a quantum of energy of electromagnetic radiation. The definition that you need to write down is the quanta of energy of EM radiation. Quantum refers to the physics of discrete amounts. And so here we are looking at a quantum of energy of electromagnetic radiation. That is just a specific amount of EM radiation. So this is all very well and good. A photon is a quanta of energy of EM radiation. Great, thanks Rob, I can put that in my pile of cue cards and learn it now. How much energy is a photon actually carrying? Well, it's related to the frequency of the radiation that that photon is a part of. We use the equation E equals hf. Energy equals Planck's constant times the frequency. Again, what is Planck's constant? Well, we plot a graph of energy on the y-axis, frequency on the x-axis, and the gradient is Planck's constant. Simple as that. Planck's constant is probably the smallest number that you will ever deal with in A-level physics. Look at it. 6.63 times 10 to the minus 34 joule seconds. 10 to the minus 34. Can you see why we use standard form yet? It features in a lot of different places, Planck's constant. You'll see it crop up here, there and everywhere from here on in the course. 6.63 times 10 to the minus 34 joule seconds. The unit has come just from this. F is in hertz. 1 hertz is equal to 1 second to the minus 1, so that will cancel off. Given E equals hf, F equals the speed of the wave divided by lambda, we could also arrive at the equation E equals hc divided by lambda, and that is fine too. If you want to just, I'm sick of working out frequencies, Rob, can I just use the wavelength? Of course you can. E equals hc over lambda. Just put that into there. That's it for photons, dead quick. Have a go at some of the tasks in part 1 and complete part A of the summary sheet. If you've still got stuff to do and you're not sure how to fill your week, don't start playing Call of Duty. Go and do some revision pages. One on the basics of waves, another on those more advanced ideas in 4.14 and 4.15.